molecule will have vibration at 0 Kelvin. So they will continuously, it will be in the periodic motion. So the molecule will have vibration. And the molecule will have, it's also having the electron, the bonded electron. A certain amount of energy is actually, certain part of energy is between it is in the bond. And some part, you know, that it is in the nucleus. So nuclear energy is the highest, it is more energy is actually of a molecule is stored in the nucleus of an atom, right? So we are not bothered about the nucleus. At least now we don't bother about the electrons. So we are only, we are so far, what will happen to the, if I give if I give energy in the form of, to the molecule, if given energy is equal to something like your energy which is equivalent to the microwave, suppose if the molecule takes that energy, so what will happen to the molecule? What will happen to the molecule? That is what we studied. So when I irradiate my microwave, irradiate microwaves radiation on the molecule, if the molecule is with the requisite condition to absorb the microwave, so what are the condition? Molecule must, to absorb microwave, molecule must have a permanent dipole moment, and molecule must be in the gaseous state. These are the two fundamental aspects. So if these two are, if the molecule is in these two conditions, then it is likely that a molecule will absorb microwave and result in, so the degrees of freedom, rotational degrees of freedom, will be for the gaseous molecule. So the molecule will actually, it will rotate fastly, maybe to, I don't know whether I can show that. I actually will show that video in the last. We don't. In the last class, I told you different rotational aspects. Right now, if I this is what we pure rotational spectroscopy. That is when I irradiate microwave, the rotational aspect of the molecule changes. That is, there is a change in rotational energy, because as I said, certain amount of rotational energy is actually allocated. I mean, certain amount of total energy is allocated for the rotation of the molecule. That actually changes because of absorption of the microwave, right? So as a result, the rotational behavior changes for a certain period of time. It is like your excitation. Excitation will not be a long, it will not sustain for a long period. It will once again come to a normal state, right? So because of this absorption of microwave, we get pure rotational spectrum. And as a result, the very important parameter of a molecule can be determined. As I said, that is a quantum mechanical parameter, because it is anything which is associated with any property of a molecule. The molecule or atom is studied only in the quantum mechanics. It's a very so that concept, though that property is actually obtained from microwave. Microwave is, though it looks like a simple spectroscopy, which is not like where NMR or any other costly spectrometer, but very interesting property of a molecule can be determined from the microwave spectroscopy, and that is what is the internuclear distance. So in that way, study of microwave spectroscopy is very much important. Then there we have seen different things. That is approximations. We actually we start with the diatomic molecule, simplest diatomic molecule. As per the quantum mechanics, the rotating diatomic molecule can be equated or approximated to a rigid rotator, which means the internuclear distance of the molecule is fixed constant. That approximation can be valid only when the molecule, when it is having when it is in the lower rotation energy, when the rotation is at the lower rotation energy. But when the molecule rotates fast, it no longer maintains a constant internuclear distance, right? So there will be so therefore, assuming rigid rotator, assuming the diatomic molecule as a rigid rotator at very higher rotation energy level, is not a correct approximation. So that is what is a non-rigid rotator, or non-rigid rotator, or what you call as a real molecule approximation, and there are a little bit energy expression. Actually, there is a change in energy expression. All those things we compared the real molecule and the rigid rotator molecule. According to rigid rotator molecule, the rigid rotator molecule approximation, it's nothing but the molecule is actually assumed that even at the higher rotating energy level, the molecule internuclear distance will be a constant one. That is not a right one. So so therefore, the internuclear distance approximation, I mean the rigid rotator approximation, as well the quantum mechanics, the diatomic molecule, that is actually valid only when the molecule is at the lower. That can be true when the rotating molecule at the lower rotation energy level. So therefore, the better approximation is a non-rigid rotator approximation. That is both the which actually which actually takes care when when the molecule is at the lower rotation energy level as well as higher rotation energy. So therefore, that approximation is a more appropriate approximation. Energy corresponding to non-rigid rotator approximation is actually more appropriate energy expression for any rotating molecule. So all this actually we have done, and there are things to be you can have expect problem. Though let us don't we should not be fixed in the rotational spectroscopy. Let us move to the vibrational spectroscopy. As I said, what is vibration spectroscopy? As I said, molecule vibrates. Molecule vibrates. So simplest molecule is a diatomic molecule, which is having two atoms. So you have a one bond or a two bond, a triple bond, depending upon the bonding. Right? Not necessary that all the diatomic molecule will have only a single bond. Right? There are diatomic molecule, which is carbon monoxide, which has a triple bond. You know that. So it is like, as I said, the the diatomic molecule actually it is in the vibration. It's like to and fro motion. So vibration is like a spring moving. Just if you extend the spring, it can. So it's like molecule is vibrating, and molecule has different modes of vibration. If you have a set of molecule, not all molecule will have same type of vibration. Some have a symmetric vibration, they have symmetric. Some may have what you call as a compression and extension. So asymmetric vibration. Some vibration may be a bending vibration. So there are different types of molecular vibration. Probably polyatomic molecules will execute those vibrations, at least for the polyatomic molecules. Right? So in general, molecule actually vibrates. Right. So as far as quantum mechanical system, we begin with a simple harmonic oscillator, or what you call as a diatomic molecule. It is assumed to be a simple harmonic oscillator, which means it's like a simple harmonic oscillation where you have a periodic motion, which like a classical physics, which obeys Hooke's law, your pendulum. So likewise, the quantum mechanical diatomic molecule, the quantum mechanics, as for the quantum mechanics, vibrating diatomic molecule is like a simple pendulum, simple harmonic oscillator. So by solving the Schrodinger wave equation of a simple harmonical oscillator, so probably you would have studied, or if the quantum mechanic just recollect your quantum mechanics, the quantum mechanics which actually solved by what you call Hermite polynomial, then you get a final by the total energy is given by h nu by v plus half, where v is a vibrational quantum number, which can have the value from 0, 1, 2, 3, etc. So these are the things we have seen. Right. So I think we have told I discuss I started different, right? The vibrational spectroscopy, and I told you certain things. So this simple harmonical oscillator or simple harmonic oscillator is a vibrating diatomic molecule. So which can as far as the selection rule is concerned, generally we'll see that. We'll try to do problem, but before that, as I said earlier, just a recap of these things which we have seen. So this is what the vibration spectroscopy, the Hooke's law, to and fro motion. This is your simple harmonical oscillator, which we have said on the other day. So this is how it's like a parabola, a perfect parabola. That is this is E is equal to 1 by 2 k x square. So this is by potential energy versus distance. So this is your internuclear distance. This the distance between the when it is extended, right? Displacement. This is your displacement, and this can be equated to amplitude also. We'll do the problems like this. So this is your lowermost energy is equal to the 0 point energy 3h2 5h2. Maybe you can see this thing now clearly, right? I think now I am magnified. So 0 point energy, and in a system, suppose if I have 100 molecules, most of them belongs to the zeroth vibration state, or which means they vibrate like the vibration energy will be, most of them will be at the V0 state, and V1 all this you have, and this is your the thing is, if I give IR radiation, so if a molecule in V zeroth vibration state, as per the selection rule, this is your selection rule. That is delta V is equal to plus or minus 1. They will move to V0 state. That is a more intense state or intense line. You get an intense IR line. Why intense IR line? Your intensity is directly proportional to the probability square or population square. So zeroth vibration state, which I called the fundamental band, the fundamental band, or any band where normally we suppose you get a signal that in IR signal, which is a fundamental band, right? Other bands 1 to 2, 2 to 3, generally at normal temperature, the other vibration energy levels or the other molecule with other vibration energy level will be less. So even though they undergo transition, vibrational energy transition by absorbing IR radiation, as I said earlier, the vibration energy changes. The vibrating molecule, the vibrates faster, then it will give you a peak that will be less intensive. This is your intensity, right? This is your in wave number, something like that. So the height of the peak is very less. So it progressively decreases, which shows the subsequent vibration energy levels are less populated. So molecule with the higher vibration energy level in a group, suppose assume if you have 100 molecules, almost most of them, maybe almost 90% of the molecule will have zeroth vibration level. Some will have zero V1, V2, etc. So when I irradiate microwave, it's probable that not only the V0 state you will have. So molecule with a higher vibration energy level will also absorb the IR radiation. They will move to the next vibration level as per the selection rule, delta V is equal to plus or minus 1. Right? Plus or minus 1, what does it implies? So you have plus 1, which means suppose a molecule is in the V0 state, they will move to, by absorption of IR radiation, they will move to V1 state. But minus, during this vibration, some other molecule in V1 state will return it will return to V0 state, or it's like an emission. Absorption leading to V1 to V0 to V1. So some will undergo what you call as the emission of energy. But which is dominating? Absorption dominates. So you get IR spectroscopy. So these spectroscopies are rotational, vibrational, or absorption spectroscopy. They absorb energy, as a result, you get a spectrum. Right? So the condition for the molecule to be IR active, as I said, the molecule must have permanent dipole moment. Like your water, you have charge separation, or like your HCl, where you have this delta plus and delta minus. Or during vibrational motion, the molecule will produce what you call as your dipole during change in vibration. So there the molecule, as I said earlier, for diatomic molecule, it will have only one stretching vibration, right? But for polyatomic molecule, it have different vibration mode as far as your this formula 3n minus 6 for non-linear molecules, and 3n minus 5 for linear molecules. right? So these are the conditions. For a diatomic molecule, it will have only one stretching, only one symmetric stretching that will lead to uh, what you call as well. So this will have a symmetric stretching. This can have something like this. So as a result, it will be stretched. It will be stretched, and it will be compressed. It will be compressed, right? So it like a spring. So therefore, diatomic molecule, homonuclear diatomic molecules are generally IR active. When it comes to homonuclear diatomic molecules are IR inactive, since these molecules do not have permanent dipole moment. And as I said, even at the symmetric stretching, dipole moment will be, there is no production of what you call as charge separation. Any dipole moment is not created during symmetric stretching. As I said, dipole moment will, the diatomic molecule will have only one type of stretching, vibration, motion. So therefore, the diatomic molecule, only heteronuclear diatomic molecules are. So this is what is that during vibration, motion, it can produce either it must have a permanent dipole moment, or during vibration, it can produce dipole thing. Suppose if you have hydrogen, so even if it is stretched symmetrically, so it will be, there is nothing is there is no charge separation. So therefore, this, dou nu by dou r, dou nu by dou r is the condition which is not. There is no, if it is not equal to zero, then it is producing dipole moment. So heteronuclear diatomic molecule, generally both it has permanent dipole moment. Even at the symmetric stretching, you will have there is a dipole moment. So this is by the operator. By you probably would have studied in group theory. So this the triple product must belong to, this is your triple product, must belong to a totally symmetric irreducible representation. So this is your dipole moment operator, and as for that, if it is for allowed transition, this the integral, the moment integral must be a non-zero value. So these are all things we said. I told you. And spectrometer, if you look at the, if you use a more sophisticated spectrometer, probably you can resolve the, or if you look, if you scan that single fundamental band, you could see different lines. That line, if you look at the normal spectrometer, you get some line. Suppose if you use a more advanced spectrometer, probably this line is made up of different something lines. So it is like your rotation lines in vibrational spectrum, vibrational lines, rotation lines in vibrational transition lines, vibrational lines. So what is this? So that is what is called a study of rotational spectroscopy, study of rotational vibrational spectroscopy. So generally for HCl, there are two types of uh, the rotational vibrational spectroscopy. As I said earlier, so it is happening because vibration energy, when I irradiate what do you call it? When I irradiate the IR radiation, that can result in what you call as both vibration transition. So this is your vibration transition. Generally, not expected. So molecule from V0 state to V1 state is your vibrational transition. That is fine. So during this vibration transition, some rotational energy is also affected, because if you look at the electromagnetic spectrum, your microwave is less in energy than your IR. So when I irradiate the IR radiation on the molecule, if the molecule absorb the IR radiation, it can definitely affect both the vibration as well as rotational aspect of the molecule, rotational property of the molecule, right? So that is what that is what you can visualize in the rotation vibration lines. Normally in a normal spectrometer, you can see the for a diatomic molecule, you get a one fundamental band and the different other transitions, like was 1 to 2, etc., which are less intense, progressively declining bands, which I have said earlier. But when I use a more sophisticated spectrometer, I could say, when I say sophisticated, I mean more advanced spectrometer. I could say that I could see that vibration lines are made up of different lines, small lines. What are those lines? They are called as rotation lines. So rotation lines, the combination of rotation lines, suppose if this is your, So the combination of rotation lines will be the combination of rotation lines will be the uh, will make you the vibrational will make the vibration line. And study of rotational spectrum, rotation lines in vibration spectrum is called as the vibration rotation spectroscopy. And the selection rule, let us not devote much time on the theoretical part. I'll stop in another 5 minutes in the theory part. I will straight away switch to the problems in the vibrational spectroscopy. uh, Okay, so this is your vibrational. So this is during this transition. I just want to show you one thing. So this is your suppose this is your one line. Assume I repeat by giving some in green line today freshly. So if I start from this, suppose a molecule in a zeroth vibrational state. If this is a molecules, these molecules are in V0 state and J0 state. And if this molecule absorb IR radiation, as per the selection rule of IR radiation, this molecule, suppose if stops here. So where this molecule is now, this molecule is in the V1 state and J is equal to 1 state. So if you look at the delta V is now it is 1. Your initial state is 0. So delta V is equal to plus 1. So obvious. It is as expected. What about the delta J? Delta J, the final is 1. The initial is, it starts from J0. So this is 1. So there is a change in rotational energy also. Initially it was J0, now it is J1. So there is a rotational energy change. Rotational energy change. So this is what you call as a result, you get a different. So it's not that only one molecule, so different rotation energy. So you have different molecule with V0 state, but different rotation energy, they will result in what you call as. So this is what you call as, they result in a bunch of lines, they called as R branches. R branches. So delta, so this is your delta, the selection rule, as I said, this is your the selection rule. Delta J is equal to R branch is equal to delta V is equal to 1, delta J is equal to plus 1, which is your R branch. Likewise, you have minus 1, which is and then 0. So generally, molecule when the dipole moment and the oscillating electrical field, the electrical field of the IR radiation and the dipole moment, oscillating dipole moment, when they are perpendicular, they give what you call as a perpendicular band, which is called as J0. J is equal to 0. So you will get only one line, the fundamental band only. But parallel bands and fundamental bands, that is what we call as vibrational spectroscopy. Let us not waste time in too much theory. So as I said, this is the fundamental band, V0 to 1 band, V1, that is the fundamental band generally. This is your frequency of the fundamental band is given by in terms of C1, and you can find out the K. K is nothing but the force constant. Force constant. So how much force I must give to disturb the vibrational motion. So how much the force constant. So all molecule K value actually differs. But when they are in the same isotopes, the K value is assumed to be same. But in the case of same value, same resembling same type of molecule, like where H2, D2, carbon carbon single bond, carbon carbon double bond, carbon carbon triple bond. So in all these cases, K value remains same, but the K value the K value differs. Sorry, carbon carbon triple bond, the K value differs actually. But generally, there's some isotope change. Isotopes, the K value is same. So K value is nothing but how much energy I must give. So this is generally the parabola. So for a different molecule. So your C double bond. So there is a comparison. So the first one is your C triple bond, C triple. So therefore C triple bond, C double bond, C is voided. It is something like this. So it is void. So displacement is larger. So the spring extends. So you can extend the spring for a larger thing. So that is for your C single bond C. That reflects when my K value is small, I can say my displacement will be larger. So it can be easily disturbed. The bond can be disturbed. The vibrational, the spring of the vibration can be extended. So that therefore your displacement will be larger. So this reflects your C triple bond C, the C triple bond C. What does that implies? So it is very difficult to stretch the C triple bond C. So your K value must be larger. So from K value, one can infer that when the K value is larger, then it requires I must give large amount of energy to stretch the thing. So your displacement will be shorter, right? So we'll stop here. We stopped here, and today we'll continue the problems and other things what we have seen as things, right? So we'll straight away do problems here. uh, as I said earlier, the okay, to begin with the simple problems. I think I have done this one in the last class, as I said. So okay, so I just started. Right, from now onwards, I'll go on the problem. So you are given the fundamental. So given thing is uh, the the fundamental band or fundamental signal or fundamental frequency, right? Fundamental frequency of fundamental band or fundamental frequency of carbon monoxide is 2143.3 in centimeter inverse. They are given the frequency in centimeter inverse. You are asked to calculate the force constant. So we'll try to find out the simple problem. We begin with the simple problem. So force constant. So this is your fundamental band. The zero implies the transition is V to 1. Right? So this frequency they are given in wave number. So therefore I can substitute here like a bar, right? Or uh, or I can multiply this in the. So therefore this can be. So you have two types of, in terms of frequency, it is 2 pi by root k by mu. This is your k. K is your fundamental the force constant. Suppose if you are given in wave number, your fundamental band can be given by 2 pi c. C is your velocity of light, k divided by mu, where mu is reduced mass. So you have to give is a single unit. The two atoms must be given in a single unit. So it is m1, m2, m1 plus m2. Depends upon the, if it is molar mass, you have to divide by the Avogadro number. Divide by Avogadro number. If it is in the atomic unit, AMU, mass atomic mass unit, you can multiply that. So everything must be at the last. It must be given in the thing. Given in so I must state that molar mass, these are the fundamental molar mass. If it is expressed in masses, mass of atom is expressed, mass of atoms in molar mass. So this must be divided by 1 Ng, Avogadro number. If it is in so this will give you, so that means this will be in the kilogram per mole. So your value will be in kilogram per mole if it is in a molar mass. If it is in AMU, so for AMU, some books they give some U, atomic mass unit. So it will be it will be at the last, it must be multiplied. 1 AMU is equal to 1.666 or 1.661 into 10 to the power minus 27 kilogram. So that is multiplied. That is, you just substitute this formula. That is m1 plus m2 divided by m1 plus m2. You need not Avogadro number. There is no need for it. Only you have to convert in kilogram. Right, now you do this problem. You are asked to calculate the force constant. So you are given the so it is your mu bar they have given. Therefore, use this formula C root K carbon monoxide. Carbon monoxide. If you do the carbon monoxide reduced formula, this is your Generally, it is your carbon will be around 12, your oxygen will be around maybe 0. This is 16 AMU, and this is another AMU, and this will be 12 plus 16 AMU. So this will get cancelled. So then you get the final expression and you have to multiply. This is your AMU. So 12 into 16 divided by this is your 28. Right? And the AMU, instead of AMU, I have to multiply this by 1.661 into 10 to the power minus 27 kilogram. So finally, I'll get my reduced mass carbon monoxide will be 1.1387 into 10 to the power minus 26 kilogram. You can do my along with me. So this is my reduced mass, and just the thing is square it. This equation one square equation one on both sides. You have to square equation one on both sides, so you get bar square. So this will be 1 by 2 pi square. So obviously this will mu c1. So therefore this can be written as k is equal to 4 pi c mu carbon monoxide, and this is your square, right? So if you substitute here, if you substitute this one, if you substitute this one, uh, you can. So here it is the this is your square, right? The this will also be square, right? This will be squared, and this will be squared 4 pi square, right? 4 pi square, and this will be reduced mass. So take everything on the other side. So this is your answer. And if you do that, you substitute everything, reduce mass 4. This is 3.14 square. Well, this will be 3 into 10 to the power 10 centimeter per second square, and reduced mass is 1.187 in 10 to the power minus 26 kilogram. And this is your frequency, as you know that they are given in what do you call this, the 2.1433 centimeter inverse. That is also square. So this square will get cancelled, right? So you have finally, if you look at this one, your value will be in the. This is how you'll just solve it. It will be around 1.186 kilogram second to the power. This is what it will get. So say a second, and divide divide and multiply by, yeah. So the divide and multiply by m, and this is nothing but Newton. 1 Newton. 1 Newton is nothing but kilogram meter second to the power minus. So therefore, the k value would be force constant would be 1.186 Newton meter to the power minus. So this is your answer. This is your answer, right? This is your answer, right? So then you continue. You can do other problems, and the next one is your uh, maybe will we have seen that your diatomic molecule, the parabola. The parabola is something like this. The potential graph, energy graph, right? This is your 0 point, and V is equal to 0. This is V is equal to 1, V is equal to 2, V is equal to 3. It goes, it can go up to, we don't know the potential energy. This is where the distance. This is your internuclear distance, RE. Right? So this is equal to, by using the formula, E is equal to h nu, V plus half So when V is equal to 0, this will be h nu. So 1 by 2 h nu. So certain books also give something like this: E is equal to 1 by 2 omega. These are both are same. Certain books gives you like this, right? So according to this approximation, this is a simple harmonical approximation. The molecule will, even at higher vibration level, even at higher vibration level, vibration energy level, molecule at the higher vibration level, it can exist. It can exist. A molecule can exist. Can exist. A molecule can exist, which means molecule will survive. But in reality, when the molecule is vibrational, when the spring is so elongated, assume a spring. If you elongate the spring, what will happen? It will stretch, and if you activate, if your vibrational motion is so fast, so what will happen? At one point, the spring may break. The vibration, when it is so fast, vibration molecule is so fast, probably that will lead to the breaking. You assume that a simple thing is, suppose if your door is flopping, ஒரு கதவு வந்து சும்மா லைட்டா அடிக்கும் போது நம்மளுக்கு ஒன்றும் தெரியல. சப்போஸ் இஃப் இட் ஃப்ளாப்ஸ் டூ மச், வேகமா அடிச்சுக்கிட்டே இருக்கிற மாதிரி எனக்கு ஒன்று ஜன்னல் உடையணும், அந்த மாதிரி நம்ம இமேஜின் பண்ணணும். சப்போஸ் அந்த மாதிரி இமேஜின் பண்ணிக்கோ. When it is vibrating too fast, molecule will break into atoms. So therefore, at higher vibration energy level, we don't know where it is, higher vibration energy level, as per the simple harmonic oscillator assumption, the diatomic molecule can survive even at higher vibration level. That is what is according to simple harmonical oscillator approximation. But that cannot be true. The molecule will, at certain higher vibration level, when the molecule vibrates so violently, the molecule will break. The molecule will break. So therefore, that assumption cannot be a correct assumption. That is simple harmonical assumption. Simple harmonical assumption or this equation. This equation cannot be applied for when the molecule is at higher vibration energy level. When the molecule is violently vibrating, you cannot use this equation for such molecules, right? So therefore you need to change. So that is what is called as the unharmonic oscillator, the harmonic approximation. So you have to change your the way of looking the diatomic molecule. Maybe the diatomic molecule, when it is calm in vibration, when it is vibrating slowly, that approximation or this equation can be, there is no problem with this equation. The same diatomic molecule, imagine if it is vibrating very fastly, violent vibration, very fast vibration, then using this equation cannot be a correct one. So you have to change the equation. So that is what is called as unharmonic approximation. Now I am approximating my diatomic molecule as a, not like a simple harmonic oscillator, or as a whole I'm treating my simple harmonic oscillator as an unharmonic oscillator. So therefore my looking the molecule itself is differing. Initially I look the molecule as a simple harmonical oscillator. So which means I have an equation that can put forth, or that can be applied both when the molecule is at a lower vibration energy as well as at a higher vibration energy. But now onwards, I look the molecule in a different perspective. I look the molecule as a different way. So that is I look the molecule as unharmonical way. That means I use therefore my potential energy curve, I use a potential, I use what you call as a Morse curve, a Morse potential energy curve. So for which the potential energy something like this, it is something like this. So this is your V0 state, this is V1 state, like molecule is vibrating at V1, V2, but at higher vibration energy level, they are in simple harmonic oscillator, we assume that the molecules are equally spaced. 3 by 2 minus 1 by 3 by 2 h nu minus 1 by 2 h nu, it is half nu. So all the vibration energy levels are equally spaced. according to diet, my simple harmonic, if I look the molecule in a simple harmonical oscillator, through that, my assumption is like a simple harmonic oscillator, the energy levels are h nu, delta E is h nu. But here, maybe the thing is, so this is when the molecule is vibrating violently. That is very higher vibration energy level. When the diatomic molecules are executing very fast vibration. So at that case, the molecule will break. So this is my dissociation. The molecule undergo dissociation. Molecule breaks. Molecule break. Molecules is actually, it dies. Molecule dies. Molecule breaks into atom. Breaks into atoms, two atoms, right? So our molecule breaks, molecule dies, right? But the simple harmonical assumption, molecule will survive when it is in the higher vibration energy, which cannot be true. So now onwards, my observation, my weighing of vibrating molecule is the simple the unharmonical oscillator. So unharmonical oscillator, therefore I use a different expression, different energy expression. The This is my unharmonic oscillator expression, so which is h nu, and v plus half. This is your previous one, like a simple harmonic oscillator, but which now the this is your h nu. Then of course you have a chi h nu, chi e into v plus half 1 by square. So this is my expression, energy expression for a unharmonical oscillator. So therefore, I use my for V0 state, suppose vibrating molecule. So what is according to this equation? So h nu, half h nu, there's no issue here, minus, so h nu, your unharmonical constant. This is unharmonic constant. This is your unharmonic constant. So unharmonic constant, which means you have to take the unharmonicity. That is why the molecule breaks, right? So it will not come to its original position. Harmonic, continuously to and fro motion. Unharmonicity, that means at lower vibration level there is some harmonicity. The to and fro motion, like a simple pendulum, it works. But when it moving to higher vibration and molecule exit higher vibration energy, there is the what you call as the periodic. There is some deviation from periodicity. So that is what is called as unharmonicity, like right. So this is v is equal to 0. So this will be 1 square, half square. This will be therefore 1 by 4. This is your v0 state. And v1 state, substitute for 1. This will be 3 by 2 h nu minus h nu xe. So this is for 1. So 1 by 3 by 2. 3 by 2 square, it will be 9 by 4. I'm just giving you. So this energy expression. So as for your unharmonical, maybe I'll color with the color thing. So this will be, sorry, I use a different color. Are you here? Are you there? இருக்கீங்களா? யாராவது இருக்கீங்களாப்பா? Hello. Can you hear me? Am I audible? கேக்குதாப்பா? Yes, please. Sorry for the inconvenience. I cannot see you and I cannot write, but I'm writing this. So this is my thing. This is your 9 by 4. Not 9 by 4. This is 1 by 4. Sorry. This is 1 by 4 h nu xe. The second line would be 3 by 2 h nu minus 9 by 4 h nu xe. Likewise, I can go on giving you. I'll give you another one line, another one energy, which is v is equal to 2. So that we'll see that fundamental band. So that is, so 3 by 2 energy is equal to 2. So substitute my equation here. So 2. So 2 is 5 by 2 then. So this is 5 by. Sorry. This is 5 by 2 h nu, and this will be 25 by 4, right? How 25 by 4? So this will be 5 by 2 once again, right? 5 by 2 square is 25 by 4 h nu xc. Some books they will give you something like this, 1 by 2 omega. For want of writing h nu in a bigger way, they write something like this, 1 by 4 omega xc. So therefore this will be 3 by 2 omega minus 1 by 4 omega xc. This is 9 by 2, 5 by 2, sorry, 5 by 2 omega minus 25 by 4 omega xc. Right. So, what is the fundamental band? What is the selection rule according to this approximation? My selection rule is delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. But simple harmonic oscillator, this is not allowed. For simple harmonic oscillator, this is your unharmonic oscillator. For simple harmonic oscillator, this is my selection rule. That is where delta, I mean, this is delta plus or minus 1 is, this is only the selection rule allowed. This is only the selection rule allowed. But unharmonic oscillator, anything is possible, right? So this is, all others are called as what you call the overtones. They are called, this is the first overtone, right? They are called as first overtones. So overtones are allowed when it is in a allowed if it look by a prism called the unharmonic oscillator. If you look by a prism called a simple harmonic oscillator, my perspective, in what way I look at diatomic molecule. In reality, simple unharmonic oscillator, this equation is more appropriate equation. So therefore, this is your fundamental band. The fundamental band is something like your fundamental band, the more intense band, which is mu naught. So what is this? This is V2 transition, right? This is because of this transition. Overtones. So if you look at this one, this is how the fundamental band, the second band, this is V2 transition. This is V2 transition, something like this. This is V2 transition, V2 transition, etc. So all these are allowed, but these are all fundamental. These are called overtones. They are called as overtones. And first, this is first overtone. They are called first overtone. This is my second overtone. And subsequent overtones. This is my third overtone. So overtones are the intensity or the energy waves, the frequency of the first overtone. Uh, sorry, first overtone. If you look at the wave number, the energy placement, the where you get, this will be twice, approximately uh, twice a fundamental band. This is your centimeter inverse. This is a placement, a centimeter inverse. This is your intensity. If I call this my intensity, so the intensity wise gradually decreasing. This is far ahead. This is far ahead because most of the molecule will be in the V0 state. The second overtone will be 3 and 4 subsequent overtones, right? So okay, now I'll show you the fundamental band difference of the simple harmonical oscillator, the energy of unharmonic oscillator, right? So therefore my E1 minus E0. What is E1 minus? E1 is nothing but 3 by 2 omega minus, this is 9. Look at this value. I'll just show you. So this is V1. V1 is, this is 9. This is 9. 9 by 4. 9 by 4 x. Omega x. Xc. Omega xc. Minus of, this is 1 by 2 omega minus 1 by 4 omega xc. So do that work. So this will become plus. So this will be 3 by 2 omega minus 9 by 4 omega xc 1 by 2 omega plus 1 by 4 omega xc. Therefore, I take these two. I'll just show you in a different color. These two. Sorry. These two. These two I'll take these two. Sorry. I'll take these two, which is equal to 2 by 2 omega, which is equal to omega. And these two are plus 1, so minus 8 by 4 omega xc. So therefore, my fundamental band is this is your fundamental band because of V0 to V1 state. So this will be the energy gap. The energy gap may be the energy gap. So I've taken my energy so far. So energy gap delta E, which is equal to h nu delta E. So this is your fundamental band, which is equal to omega minus 2. This is 2, right? 2 omega xc. So therefore, this is nothing but omega xc. This is nothing but, if we take omega outside, this is 1 minus 2 omega, not omega. This is omega xc. If I show it like this, in terms of energy, I can explain in terms of the same thing in for my. I'll do it for a reason. So omega is nothing but h nu. You know that. So this is 1 minus xc, right? So this is what is your answer. This is what is your answer. So therefore, what is your omega? This is your thing, right? Xc minus 2 omega xc. And delta E is nothing but delta nu bar h, which is equal to h nu into 1 minus 2 xc. So this two get cancelled, and this is your fundamental band. Is nothing but the fundamental band minus 1 minus 2. Of course, this has to be xc. So the fundamental band is nothing but mu naught minus mu bar 2 xc. So this is another way of giving the expression. Okay, we'll do problems here. The simple harmonic oscillator. A simple problem. This is you're looking the molecule with a simple harmonical oscillator. So we'll do problems like I'll give you the data. The fundamental band. They are given data. I'll leave you by 12:40 in another 20 minutes. Fundamental band. We'll do some problem. How much we cover, we'll say fundamental band, first overtone. So these are the data given. Second overtones. For HCl, they are given. This is for HCl. The fundamental band is 2886. The first overtone is twice the fundamental band, approximately 2668. All these are in centimeters. And fundamental band they have given it is 8346. I mean second fundamental band. So these are the data they have given. You are asked to calculate the h nu. You are asked to calculate the omega E, the oscillator, the frequency, the h nu, and force constant and unharmonic constant. These are the things you are asked to calculate. You are asked to calculate these things. right? So these things you are asked to calculate. Force constant, your frequency, the h nu, and unharmonic constant. So these are the things you are asked to calculate. So how will you calculate these things? By knowing the fundamental band and overtones. So to calculate the harmonic oscillator, you need these data. That is the thing you have to remember. One can calculate the unharmonic oscillator, provided I must know the fundamental band, overtones, all those values. Only then I can calculate. So this is the equation. So this is my fundamental band. So omega, the fundamental band is nothing but this is E into 1 minus 2xc. This is what I have discussed so far. And this is your the second. So this is as a result of what? 0 to 1 transition. And the second is this is equal to 24286 centimeter inverse. This is fundamental band. This is fundamental band. The first overtone, this is your first overtone. This is because of 0 to 2 transition. So it is VE into 1 minus 3xe. If you do the difference, you will find out the 3xe. This is around 5668 centimeter inverse. So therefore, I must take these two. That is, in a simple way, this is my WE minus 2 omega E. This is XC, which is equal to 2886 centimeter inverse. This is equation 1. The second equation, omega E minus 3 omega E XC, which is equal to 5668 centimeter inverse, which is my equation. So what I do is, equation 1, I multiply thrice. If I multiply by 3, if I multiply by equation 3, I will get something, some values. I get values. And subtract the equation, the equation 2. Subtract the equation 2. So multiply equation 1, multiply 3, and so if you get value some, then you get some value. Then subtract with equation 2. If you do this, so first is multiply equation, multiply 2, then followed by subtracting it. You will get, if you solve this, you will get omega E, you will get this value, omega E, that is 2990 centimeter inverse. What is omega E? As I said, this is what is your omega E. Right? So by knowing omega E, I have an expression that is my unharmonic constant. It is called as unharmonic constant, which is omega, the chi. This is not x, chi E, which is equal to omega E divided by 4 dE. What is dE? Which is your the spectroscopic dissociation energy. It's called a spectroscopic dissociation energy. Spectroscopic dissociation energy is nothing but D. Spectroscopic thermodynamics. It's a dissociation energy. So dissociation. I'll show you what is it. So if you now substitute the so from this you can calculate, or you can find out, or if you substitute that, sorry, this can be this, you can get this one XC from by substituting WE in one of the equation. Maybe in equation, if you substitute the WE in equation 2, because equation 2 you get XC, so unharmonic oscillator can be calculated. So by knowing unharmonic oscillator and by knowing now I know these two, that is omega E. So these two, I can calculate what you call a spectroscopic dissociation energy. DE can be calculated. So from where dissociation energy, so this is nothing but the dissociation energy is nothing but omega E XC 4XC. So by this equation, I can calculate this is by uh, the the 2990 centimeter inverse. If I calculate this, and if I calculate my by substituting this, I get my XC unharmonic oscillator, something like this. You can try this one. So by knowing this, I can calculate the 4 into 0.0174. I can calculate dissociation energy. So what is this dissociation energy? So this is the energy required to break the molecule. Energy required to break the molecule. So you have two types of. So if you look at the Morse curve of a if a diatomic molecule is assumed as a simple unharmonical oscillator, so 0 point energy. So at a very higher vibration energy, they are so compressed, they are so closed, and this is your convergence. We see at when the molecule is at this vibration energy, it will break, and this is your DO, the thermodynamic dissociation energy, and this is where DE. This is your DE, which includes everything. Right? So dissociation energy of molecule can be calculated from this equation. Right? And I can calculate the force constant, Ke. You know that this is a formula, 4 pi square, C square, the omega square, that is your frequency omega square. Then you have reduced mass of HCl. This is all your for HCl. So substituting this, you will get 5, 6 omega only is the thing. And the reduced mass you can calculate for your HCl. Right? If you substitute all those things, it is Newton. The force required to extend 1 meter distance. The bond is elongated to 1 meter distance. The force required. So this much of force is required. Right? So this is your problem. Generally, unharmonic oscillator problems are asked like this. Unharmonic oscillator. So you will be given an unharmonic constant can be calculated by taking two equations, and you have to convert it. From this, you have to calculate the h nu or omega, and from that unharmonic oscillator. By knowing the unharmonic oscillator, by knowing h nu naught, or h nu naught is nothing but this is what is your h nu naught, right? So that I can calculate the what you call as your force constant. Then the other problems are something like the as I said, the thermochemical dissociation energy and spectroscopic dissociation energy. So DE is nothing but so DO, the 0 point energy, distance between the convergent limit, and DO, the 0 point energy, that is called as your thermochemical. They are called as thermochemical dissociation energy. Thermochemical dissociation energy, and that is called a spectroscopic dissociation energy. So which is equal to dE minus 1 by 2 h nu. What is this 1 by 2 h nu? Which is nothing but your 0 point energy. So this is your total energy, and this energy, this is your 0 point energy. Maybe this is your 0 point energy that will give you, right, dU. That is what is, right? So this is nothing but your spectroscopic dissociation energy. Spectroscopic dissociation energy. Supposing if in this problem we are calculated with dE. So by knowing dE, by knowing half h nu, so 0 point energy, I can calculate what is called as your thermal energy. This can be calculated provided if I know this one. So for your HCl problem, I can calculate this by substituting my dissociation energy. What is the dE? If I calculate this one, I get dE, my dE value. Substitute here, and half h nu. This is my then the 0 point energy, the frequency, the 0 point energy. So from this I can calculate the right dissociation energy. So calculate the ratio of frequencies. Calculate the ratio of 0 point energies of H and maybe DD. A simple problem. Assuming my force constant are same for both molecules, are same for both the molecules. So how to do this one? So 0 point energy is nothing but half h nu, which is equal to h by 4 pi your frequency. This is I'm substituting. So h by I'll begin by 1 by 2. What is my frequency is 1 by 2 pi. This is for my frequency into k reduced mass. So therefore I can very well write h by 4 pi. My reduced mass equation now turned to be like this. So this is my reduced mass equation. I mean not reduced mass, my 0 point energy equation for any molecule. That this is my reduced mass equation by assuming it as a simple harmonic oscillator, because I use this equation because for simple harmonic oscillator, right? Okay, so now for only thing is my k value same. These are all constant. All these are constant. So they are asking the ratio, 0 point energy ratio. As I said earlier, I'll leave you by another 10 minutes. 12:40 I leave. I'll try to cover one or two problems. So they are asking you to 0 point energy of hydrogen and the 0 point energy of deuterium. So all these are constant. If I substitute here, this is my energy expression. So if I substitute the thing, I will have only the thing. This is what is the reduced mass of DD divided by reduced mass of HH. This is the only difference I can have. So even here, reduced mass DD is nothing but it is like 1 plus 1, right? 2. The mass of this is deuterium is 2. So it is 2 into 2 divided by 2 plus 2, right? Here it is like, right? This is like something like this divided by 1 divided by 2. So your 2 will come here, right? So as a result, so just look at this. This is everything in the root. So this will be therefore, so 2 into 2. So this is how. So it will be 4 divided by 2 into 2. This is 2 plus 2. 2 into 2, 4. This is 2 plus 2, which is also 4 into 2. So you get something like this. So finally you get 2. It is your root 2. So root 2 will be, so your energy, 0 point energy of H2 and D2 will be equal to 1 point. Root 2 is root 2, which is equal to 1.4 times. So therefore, your 0 point of, which is greater, your energy of 0 point of energy of H2 is greater than 0 point energy of D2 by 1.42 times, right? So this is a simple comparison. And you can do the problems something like your isotopic substitution also, which I told you. Okay, so I told you about the k values. I told you about the even say, okay, so this can be so comparison, the fundamental band. You can extend this into fundamental band. So they are given the fundamental band of HBr, fundamental band of uh, DBr. This is our fundamental band. You are given you are they are given one fundamental band that is assume the fundamental band of the you are asked to calculate the fundamental band of anything. So the only these two, if you look at the fundamental band, they can be equated into the reverse, the reduced mass of DBr and reduced mass of HBr. If you do this reduced mass, it will be once again, as we have seen, it is root 2, which is equal to 1.4. So fundamental band, it is fundamental band of HBr will be twice the fundamental band of DBr. This is your another expression. So fundamental band. This is your not one exactly 2. Sorry, it is 1.42 times the fundamental band of HBr will be fundamental band of DBr. So isotopic substitution. This is fundamental band in terms of fundamental band. Fundamental band. HBr and DBr. By knowing one value, I can find out the other values. So what is the fundamental band of? If I know the HBr fundamental band, I can find out the fundamental band of what is the DBr fundamental band. Or if I know the DBr fundamental band, I can find out the HBr fundamental band by this isotopic substitution. Isotopic substitution. Then there is last problem. Maybe amount of time. This is my last problem. Maybe we'll continue one or two problems in the next class, and then we'll move to what you call as the Raman spectrum. Supposingly, this is the problem. Calculate the ratio of molecules. As I said, normally the ratio of molecules, the molecule, calculate the room temperature, that is at 298 Kelvin. That is calculate the population of the carbon monoxide, because carbon monoxide we are doing continuously. It's a population. This is population of carbon monoxide in V is equal to 1 state and V is equal to 0 state, or relative population. So which is relative to V level, V is equal to 1 level, relative to V is equal to 0 state, and given that, so they are asking you which is more populated, V is equal to 1 state and V is equal relative to V0 state, right? So given that, so they have got the fundamental band they are given, which is 21 in V 69 centimeter inverse. They are given the value. This is what is it. So calculate the V01 population of V1 state. Population of V1 state. So they have given V relative to V0 state. So we'll see. So they are given population ratio. So use this formula generally. This is your Boltzmann equation. Maxwell-Boltzmann equation. Use Maxwell-Boltzmann equation for vibration energy level calculation for population. Any population energy level, generally we use this equation. So V is equal higher level. V is equal to 1 state. This is V equal to 0 state, which is equal to degeneracy of the state delta E, because this is common, but this is degeneration 0. Delta E divided by KT. This is an expression for this problem. Do you know the degeneracy of vibration energy level? All vibration energy level, degeneracy is equal to 1. But when it comes to degeneracy of rotation energy level, this is degeneracy of vibration energy level, vibrational vibrational energy level is always approximately 1. But remember, recall your degeneracy of rotation energy level. What is that? Rotation energy level is, we use a formula 2j plus 1. So depending upon the thing. So it is, here it is 1. So it is like our the ratio 1 by 1 delta E divided by dt. So use a formula. So this is your delta E is equal to so exponential. So minus. So I can use, instead of delta E, I can use a formula. It's okay. So I use this one. So my exponential frequency is 6.6626 in 10 to the power minus 34 joule second. This is for your Planck constant, Planck thing. Then you, this is for velocity of light. This is 10 centimeter per second. Then this is your fundamental band. Omega is your fundamental band. Fundamental band. The fundamental band is 2196 centimeter inverse divided by Boltzmann constant is 1.38 10 to the power minus 23 joule per Kelvin. The temperature is 298 Kelvin. If you solve this, maybe for this must be in, everything must be, should cancel. These two cancel. Per Kelvin, Kelvin should be cancelled. Second per second will get cancelled. Centimeter. So you can write. So you are exponential. You do this problem, you get ratio. So 0.0020. You just check. So this is equal to 1, but n v is equal to 0. So therefore, this is very, very small. This is very, very small, something like 2.8 to the power minus 5. That shows this numerator is very small, the denominator is very larger. Then only you get this value. Numerator is very small. Then your denominator is very large. So your denominator is very large. Therefore, your V0 state is not 25. V0 state is very much populated. So 1 will be equal to 2.8 into the power 8 into the power minus 5 times n0 state. Right? So at 25 degrees, your n is equal to more populated and is equal to 1. So your V0 state. This is V0 state. This is V0 state, V1 state. Most of all people will have this kind of energy level. Only a small people with the n will have this V0 state. This will progressively decrease. When I increase the temperature, suppose 25 degrees Celsius, suppose if we increase the temperature to 2 degrees Celsius, what will happen? And there will be change in temperature. I do that. I get something like suppose if I heat to say 1 degrees Celsius. Same formula, you have to use the same formula. This n by n0. This is your 1 by 1 e to the power minus, right? So you substitute the fundamental band is assume for the sake of the fundamental band. If you, I'll just show you the HC, the fundamental band, right? The fundamental band is, this is your fundamental band divided by K. T is your 1000 K. So your exponential, that is n by n0, so this is your exponential. This is minus 6.626 in 10 to the power minus 34 joule second, right? Into this part is where 3 into 10 to the power 10 centimeter per second. Then omega, as I said earlier, 214. You just try the same thing, 2169 in centimeter inverse divided by 1.38 into 10 to the power minus 23 joule per Kelvin. And this is temperature is 1000. That means 273 Kelvin. If you do this, definitely there will be some shift. Some of the molecule in the zero state, V0 state, will be migrating to V1 state at this temperature. But not, but still then, till I mean, even then you will have what you call as molecule not only vibrating to V1 state, they will be migrated to V2 state, etc. So right, so this will be there will be definitely there will be an increase in the ratio. The energy, the ratio will be increasing. You can do this, and as I said, now the population. This is at 1000 degrees Celsius. The V0 state and V1 state, V2 state, V3 state. So consider there will be some increase in number, but not progressive. But this state at this state, even this as for the selection rule, delta V is equal to plus or minus 1. So you as usual V0 1, then V0 1 to 2, V2 to 3, etc. So this will be fundamental band. So you will have some, there will be some intensity. So this is your V0. This is from V0 to 1. This is 1 to 2. This is your V2 to 3. It goes right. So at higher temperature, these, but at lower temperature, at the room temperature, you will have this is your thing, and this is all small one. But at higher temperature, the intensity of second line is reasonably increased, and this is called as hard bands. They are called as hard bands. So the population of the vibration energy level increases at the increase in temperature. Right? I'll stop here. Maybe in the next class we'll continue. I don't know. In the next class we'll continue from these problems, and we'll move to the next molecular spectroscopy, which is your Raman spectroscopy. Right. So thank you for your patient listening.